Hello, so today we will talk about Gaussian elimination. So first of all, let me define the notion of system of linear equation. So we start by a definition. A system of linear equations has n equations and m equations and n unknown of the form S. So S will represent the set of this equation. They are linear, so linear means that these are equations of the type a11x1, a12x2, 3 dot. The last one, a1n xn equal b1. Okay, so this is equation 1. The last equation, so we have m equation. So we start with am1 x1 plus amn xn equal. So how many equations do I have? I have m equations, so bm. Okay, so this is a system of m equations linear in the variables xi. So here the aij and the bj are all real numbers. Now, remember the previous chapter about matrices? If we set A equal the matrix with entries aij, B the column vector with coordinates the bj, and X the column vector with coordinates the xi, then S, the system S, is actually equivalent to the following equation of matrices, namely A times x equal B. In particular, the set of vectors x, x1, xn satisfying this equation that I call star coincides with the set of solutions of the system of linear equation S. So to solve the system is exactly to solve an equation of matrix. Now to succeed to solve this equation, we will use the so-called method of Gauss, German mathematician of the 19th century, and that is called the Gaussian elimination. So, what is this method? First of all, we are going to use a matrix called the augmented matrix that is gathering all the information about the system S. Let me So let's say that to find these solutions, will use the following matrix. Okay, so first of all, we take, in the first part, we take A. Then we will write a vertical bar and we will write the other delta B. This is called, so this amount to write down A11, and here you have A1N, and then B1, AM1, AMN, and then here you have BN. Okay, so this is a so-called augmented matrix. So you augment the matrix A with the data of B, and you call it the augmented matrix. Okay, so the idea of Gauss is to practice on this augmented matrix some operations that will not modify the set of solutions. Such operations are called elementary row operations. Why row? It's because we will only work on the rows of the matrix and not on the column. So you never work on the columns, only on the rows. So let me introduce the following definition. We will call elementary row operation or operations. So we will call elementary row operations one of the following operations. First, operations 1, we will swap two rows. Now observe that if you have your system of linear equation, you want this and that you have a solution, then it means that this solution satisfies simultaneously the m equations. So it doesn't matter if you consider equation 1 first or equation 2 in second, you can swap them, it will give you the same set of solutions. So this operation definitely will not change the set of solutions. The second one, you will multiply a row by a non-zero scalar. Again, as you know, if you have an equation and you multiply on both sides this equation by a non-zero scalar, you will find the same solution. Okay, so this operation also doesn't modify the set of solutions. The last one, we will add any multiple of one row to a different row. Okay, this is a little harder to imagine, but this is actually true. This operation does not modify the set of solutions. We will use also the following notations to remember what kind of operation we use. So notations. Okay, for O1, swapping of two rows, we will use the following notation. If you swap row I with row j, you will write like this. Row I is swapped with row j. Now, operation 2, you multiply a row by a non-zero scalar. So you will write first the row that you are going to modify, let's say row I, and you multiply this row by the scalar lambda. So you will write like this. O3. So what is this operation O3? I modify one row, and what do I do with this row? Well, I add a multiple of another row. So it will be something like lambda times Rj. Okay? It means that you modify Ri and you replace it by Ri plus lambda times Rj. Please use these notations to preserve the memory of the operations you are doing on the augmented matrix. Okay. Another definition. We say that two matrices B and C are row equivalent to each other and we use the symbol B equivalent to C or tilde C if we can get C from B by performing a finite sequence of elementary row operations. Okay, so let's think about our original problem. We want to solve the system of linear equations. We transform first this system into one equation of matrices. Then we work on the so-called augmented matrix, where we gather the information of the matrix A on the left-hand side, a vertical bar, and the little coordinates of B on the other side. Then Gauss, the method of Gauss, which is called the Gaussian elimination, will use these operations that are not modifying the set of solutions. Okay? And then we will say that if we start from an augmented matrix and we do a finite sequence of any of these operations, we get a new augmented matrix, and we will say that they are row equivalent. Okay? So it is actually obvious that so we have the following result. If A, B is equivalent, row equivalent to A prime, B prime, then the solution of the system S corresponding to the augmented matrix AB coincide, so the set of solutions will coincide with the set of solutions of the system of linear equation S prime associated to the modified augmented matrix A prime B prime. Yeah, this is obvious because you are doing a finite number of operations, and each time you do one operation, you don't modify the set of solutions. Okay, so obviously you will get the same set of solutions. Okay, so we can transform our system into another system by using this elementary row operation. What is the purpose of that? The purpose of that is that starting from a quite complicated matrix and doing these elementary operations, we want to transform this augmented matrix into something more simple. A matrix, an augmented matrix that will be easy to find the solution. Okay, so let's have a look on the so-called Gaussian elimination. So I repeat, I want to transform by some operations, these row elementary operations, I want to transform my augmented matrix into something simpler. So let me now define what I mean precisely, mathematically speaking, by simpler matrix. Such matrix will be called, so definition, it will be called, so a matrix is called a row, so reduced row echelon form. Okay, so we'll use the abbreviation RREF. If the following conditions hold. Okay, so I have in fact 4 conditions to be satisfied for this row elementary matrix. The first condition is that if there are any rows with 0 as only entries, then these rows are at the bottom. The second condition, so we will explain later all of these conditions one by one. The second condition is that for any 2 other rows the first non-zero entry, the first non-zero entry in the lower row must be strictly further to the right than the first non-zero entry in the upper row. This is the second condition. The third condition, the first non-zero entry of the non-zero rows is always a 1 and is called a pivot. Finally, the last condition, the only non-zero entry in the column containing a pivot. This will be called a pivot column. So the only non-zero entry in this column is the pivot. Okay. When a matrix, an augmented matrix in fact, satisfies these four conditions, we will say that it is reduced row echelon form, or you can say RREF. Now let's give an example and look at the meaning actually of this condition A, B, C, and D. Okay, I will keep the condition here, and let's take the following example. We consider the matrix 1, 2, 0, 0, vertical bar, one more, 3, vertical bar 2, and then 0, 0, 1, 0, minus 1, 4, 0, 0, 0, 1, minus 2, 3, 0, 0, 0, 0, 0, 0. Okay. So actually, this is RREF. Now let's check that the four conditions are actually satisfied for this matrix. Okay, what about the first one? So the first one is that if there are any rows with 0 as only entry, they should be at the bottom. Okay, so here this condition is obviously satisfied because there is indeed a row with entries only zeros, but it is at the bottom of my matrix, bottom. Okay, so condition A is okay. What about B? B is a condition that I need to check for any two other rows. So it means that I have to check this condition B for any pairs of rows. So I'm going to check it. So condition B, I need to check it for row 1, row 2, row 1, row 3, row 1, 2, 3, 4. Yeah, so in fact, it is enough to check B for the non-zero entries. And therefore, I don't need to consider here the row 4 in this case. But, so what do I have to do? I still have to do row 2, row 3. And yeah, that's it. Row 2, row 3. So I have to check it 3 times. Okay, now let's read. For any 2 other rows, so I consider in each case this pair. The first non-zero entry in the lower row. So if you take a pair of rows, one is lower than the other one. Row 1, row 2 is lower. Okay, so the first non-zero entry in the lower row. So I consider row 1, row 2 here, okay? The first non-zero entry in the lower row, this is here, must be strictly further to the right than the first non-zero entry in the upper row. So what is the first non-zero entry in the upper row? It is this one. The question is this entry further to the right compared to this one? Yeah, this is absolutely true. It's further to the right. Okay? So, condition B, okay, for this one. Now I need to check it for all. So now what happened? I want to check it for R1, R3. So I don't consider anymore this. Okay. Now this time I consider row 3. So the non-zero, first non-zero coefficient is here. Is it further to the right than this coefficient? You can see that it is. Okay, it's further to the right. So B also okay for this one. Okay, and the last one I'm going to consider this time row 2 and row 3. So row 2 here, the lower coefficient is further to the right than the upper coefficient. This is also true. So B is okay. So if condition B is okay for all possible pairs, and you can consider only non-zero rows, okay, then the condition B globally will be satisfied. Condition C, okay. So condition C is saying that the first non-zero entry of the non-zero rows is always a 1. Okay, so the non-zero rows here are row 1, row 2, and row 3. Now we consider the first non-zero coefficient. First non-zero coefficient here we go. Is it a 1? Yes, it is a 1, and therefore condition C is okay. Finally, the last condition, the only non-zero entry in the column containing a pivot. Okay, so remember, these entries, these special entries, they are the first non-zero entries of each row. They are called pivot, and they are equal to 1. Now, what is a pivot column? Well, pivot column will be this, will be pivot column 1, and this will be a pivot column 2. And finally, this will be pivot column 3. Okay, so as you can see, some other columns are not pivot. Okay, only the columns containing a pivot are called pivot column. Now, the condition D is that the only non-zero entry in the column containing a pivot is the pivot, which means that all other entries except the pivot should be 0. This is true, this is true, and this is true, okay? So condition D is also okay. Okay, so as you can see, RREF is a kind of matrix like stairs. Globally, it's like if you are going down some stairs, so, and it finished by some zeros. The lengths of the stairs are not necessarily equal to 1. The pivot doesn't need to be next to the other pivot, but they are always on diagonal, further to the right. Okay, further to the right, but not necessarily next to the first pivot. When you have this kind of matrix and full of zeros here, below the pivots, then this will be called a RREF. Let me give further definitions. A pivot column corresponds to a variable of the associated of the system associated to the augmented matrix called a pivot variable. And second definition, so the important word is pivot variable. We are going to explain on this example what is a pivot variable. And the non-pivot variables are called free variables. Free variables. Okay, so on this example, what does that mean exactly? Okay, what is the meaning of one example? Okay, so let's consider this augmented matrix. The augmented matrix is 1, 2, 0, 0, 3, the vertical bar, 2, 4, 3, 0, and then I have the 0, 0, 0, 0, 0, 0, and then I have 1, 0, 0, then I have 0, 1, 0, and finally I have -1, -2, and 0. Okay. So this is the same. It's RREF, and we have seen that the pivot columns are here. Now, this is an augmented matrix. So it corresponds, we can associate to that, in fact, a system. How do we do that? We are going to name the variables. So the variables correspond actually to the number of columns before the vertical bar. So namely here we have 1, 2, 3, 4, 5. We have 5 columns before the vertical bar, which means that we will have to use 5 unknown. Okay, so I'm going to denote them x1 to x5. Okay. Now, this augmented matrix, let's say A, B, it corresponds to the following system. So, first coefficient is 1 times x1 plus 2 times x2. Then I have 0 times x3, etc., plus 3, again 0, sorry. Okay, so 0 x4, and then plus 3 x5 equal 2. Okay, I can do that for all of them. For example, the last line is really 0 equals 0, as you can see. Okay, this is the system. Then, what are the pivot variables? So the pivot variables well, simple. They are the variables corresponding to the columns here. So first column is corresponding to the coefficient in x1. So x1 is definitely a pivot variable. x2 is not. x2 is not. x3 is. And then x4 is also a pivot variable. Therefore, we can say that the three variables in this case are x2 and x5. This will be a critical knowledge to remember when we solve our system of equations. Okay, so I repeat. We start from a system, then we associate an augmented matrix, and then we are going to use an algorithm where we will use only operation on the rows. These operations are called elementary row operations of 3 types. And at the end, we want to obtain something more simple, which is called a RREF matrix. So a fundamental fact is that I will not prove, but let's call it a fact. For every augmented matrix A, B, there exists a RREF augmented matrix A prime, B prime, such that A, B will be row equivalent to A prime, B prime. Okay, so this theorem is saying that after a finite sequence of row elementary operation, I can transform any matrix into a RREF matrix. Okay, so this A prime, B prime will be denoted RREF of AB. That will be our notation. So we have constructed some kind of operation which is called RREF, such that the input is any matrix and the output will be a RREF matrix. Now, what about the numbers of solutions? Number of solutions of the system. system of linear equation. Okay, so first of all, if we have in the augmented matrix a row with a non-zero entry and zeros everywhere else, then the system has no solution. Such system is called inconsistent. Inconsistent. Okay, so when you have, so you can have no solution at all, and you will call the system inconsistent. Now another case. So when that doesn't happen, otherwise, the system is said to be consistent. So when it is consistent, what can happen? Well, if there are no free variables, then the solution is actually unique. And if there are free variables, then the number of solutions is, in this case, infinite. Okay, we will end here, and next time we will finish the method of so-called Gaussian elimination, start with the system and show how we can actually solve this system using RIF4 and the row elementary operations. Thank you.